You guys probably find it less funny than I do, but you know, I guess you guys are the ones who need the recordings. Let's adjust this down just a smidge. It looks like we're down to about half the people show up for lectures by now. I mean, if they're recorded, I guess that's fine. It makes me a little bit sad though. But that's also not surprising, even in real courses, like not online courses rather, that the same happens as well. About 3 weeks in, you get half the people showing up. So, you know, it's not a big deal. Right, anyway. So the midterm is, how the midterm will go is the midterm of the exam, the final exam will go, are still up in the air. The department is trying to establish kind of department-wide rules for how to do these online exams. And what they're leaning towards, it seems like, is open note, open book, but no use of a computer. So what that'll entail is, if you guys are taking digital notes, you'll need to like print them out, which is a bummer, but it's to prevent people from cheating, basically. But anyway, I'll talk more about that when I know more. There's an email chain going back and forth, and I'll update you guys once we have something ironed out. Anyway, so last time I left you off on a literal cliffhanger. The question is if you have two masses suspended by a rope connected to a pulley on an inclined plane, what is the minimum value of capital M, this block here? Oh, I never actually, it's still gonna probably misbehave. Harrison, I'll answer that later. What is the minimum value of M so that neither block stays still? So that neither block moves. And note that there is friction, so like even if capital M and little m were perfectly balanced, if there was no friction, friction gives you a little bit of wiggle room, so it'll give you a minimum value of M and a maximum value of M before it can move, because that friction can kind of buffer against extra mass. So let's just start. So we start with force diagrams. So I'm going to draw a force diagram for capital M. And so capital M looks something like this. We have our block at some angle. We have gravity going straight down, force due to gravity. We have friction going to the left, and I'll explain why it's friction going to the left. We have tension going towards the right, and we have the normal force going straight up from the inclined plane. So the first point of order is that friction is basically, the friction is going to the bottom left because we are trying to see what the minimum value of capital M is. And I can explain that more. The idea here is that if M was smaller than the minimum value, then it would, then the block would move up. So what this friction is doing is it's preventing it from moving up. Hence, the frictional force must be down and to the left. If this question was instead asking what is the maximum value of capital M, the friction would be going to the up and to the right rather than down and to the left. All right, so now let's examine the components of the acceleration for this block. Oh, by the way, this angle here, that angle is theta. And you can do some basic geometry to verify that. The components of the acceleration are, we have the acceleration in the, oh, I should give you coordinate systems. I'm going to use the coordinate system that is aligned with our block. So it's a rotated coordinate system. And now this might seem weird to you guys, but you guys have to get familiar with using non-standard coordinate systems because they can make your lives a lot easier sometimes. So in this coordinate system, the x direction is up and down the plane, whereas the y direction is perpendicular to the plane. So the acceleration in the x direction is, well, by definition, it's the net force in the x direction divided by the mass. And the acceleration in the y direction is also the net force in the y direction divided by the mass. Now, what we want to solve is we want to solve the case where neither block moves. What that implies is that, so no motion implies the following. It implies that ax is 0 and ay is 0, i.e. it's not accelerating at all. And from Newton's first law, an object without acceleration doesn't move if it's already stationary. Further, we can actually compute the net force in the x direction. Well, what are some terms? We have the tension force from the rope. That is certainly a force in the x direction. We have the static frictional force to the left, which is negative, so that corresponds to a negative, or a force in the negative x direction. Then we have to do a little bit of trig just to get the x component of the gravitational force. In this case, it's Fg capital M times sine of theta. You can figure that out by seeing that the diagram looks something like this. Or the force is straight down. We have our y-axis and our x-axis. If this is Fg sub m, then this is Fgm sine theta, where this angle is theta. Right, so that's the force in the x direction. The force in the y direction, again, this is on the first block, on the big block, is just n minus Fgm times cosine of theta. And again, you can figure out that angle right from the get-go. So what we have then is we have the following equations. We have that T minus F sub s minus Fgm times sine of theta equals 0. And that's using Newton's second law, applying to the force in the x direction and the acceleration in the x direction. And we have n minus Fgm cosine of theta equals 0. And so these are our two equations that we're going to look to solve. But we're not done yet. Remember, I talked a little bit about, well, actually, let me back up. There's also another block that we have to worry about. We have the little block m, or the block little m rather. That has the same tension force upwards as the big block capital M had up and to the right, because tension is preserved across the across the ropes. And we just have the force of gravity on little m down. And so again, if we want stationary motion, we get the acceleration in both directions is 0. Sorry, stationary, no motion. And so, well, there are no forces in the x direction, so we can just ignore that term. And so we have F net in the y direction over m has to be equal to T minus Fgm. Again, we're going to use the standard coordinate system. You can use different coordinate systems for different, you can use more than one coordinate system in a single problem, as long as they are separated by the, as long as each free body diagram has its own coordinate system. Yes, Cody, the T's are the same, and that's because tension is transmitted equally through a rope. So the same force that is applied on the mass capital M is it's the same force that's applied on the mass lowercase m. And that'll be true because ropes are massless, or the ropes that we consider are massless. Once we start worrying about ropes that have mass, that will no longer be true, but we can adjust the calculations accordingly. Right, so we take this, we set these two things equal, and then we get that T minus Fg little m equals 0. So now we have 3 equations. So let's count variables, right? So we're not really interested in what theta is. We can just leave that as some constant. There's force G sub m. There's the tension force. There's the normal force, and there's the frictional force. And then there's force G sub little m. Now, there's some trouble here because it looks like that there's 5 variables and 3 equations, right? The 2 gravitational forces, both of which depend on the mass. And then there's tension, frictional force, and the normal force. Fortunately, we do have one more equation, and that is the constraint. So the constraint here is that, and this is separate from the physics of the problem, or rather this is separate from Newton's laws. The constraint here is that if we want to find the minimum value of m, that equates to the static frictional force being the maximum possible value it can be. Remember that the static frictional force changes its values depending on what force is applied to it. But if m is sufficiently small, then the gravitational force helping pull capital M down is smaller, and hence we have to have a larger static frictional force. And when m is at its minimum value to remain stationary, the static frictional force will be at its maximum value. So remember that the formula for the magnitude of the static frictional force is mu sub s times n. And in this case, this is the normal force of the block with capital M inside of it. So in our case, the minimum mass M corresponds to maximum value of Fs, which means that Fs in our case is equal to mu sub s times nm, not just and that should be nm, by the way, not just less than or equal to. So now we have 4 equations and 5 variables. Now, unfortunately, that's all we get. However, what we can realize is that if we doubled the mass of both blocks, that shouldn't affect that shouldn't affect what our answer looks like, right? If everything else is the same but you doubled the mass of both blocks, it should still remain stationary. And that's just basically what units are you using for your mass. And so what we're going to find is that lowercase m, the mass of the smaller block, or the mass of whatever block, is going to show up in our answer for the minimum value of the mass of the mass capital M. And that's okay. That just says that if you double lowercase m, you'll double uppercase m. So that's okay. So now we can go on and we can solve. So there's just a quick recall here. Recall that Fg capital M is just capital Mg, and Fg lower m is just lowercase mg. This is just the formula for the magnitude of the force, of the gravitational force. And so now we can go and we can actually plug in and solve. So we have basically 4 equations, 5 variables, and we just want to solve, and we want all of our equations to show up in the form of having a little m floating around. But there's just a whole bunch of algebra that you can do solving these. At the end of the day, I'm not going to go through the algebra. At the end of the day, you end up with the minimum value of capital M is equal to lowercase m, not surprising, divided by mu sub s times cosine of theta plus sine of theta. That's the answer you get. So what does this tell us? Well, for one, as I mentioned, if you double lowercase m, you double the minimum value of uppercase m. That's not surprising. Also, if the angle was, say, 90 degrees, meaning that it was just 2 masses hanging from a pulley, well, cosine of 90 degrees is 0, sine of 90 degrees is 1. Well, so if they're 90 degrees, there's no normal force, which means there's no friction. So all of that implies is that then lowercase m has to be equal to uppercase m in order for them to balance. And that makes sense. If you have 2 masses hanging from a pulley, they have to be of equal mass, otherwise they won't balance. And then you can check out other limits, but that's the gist of this problem. All right. So I do want to make sure that I go over a quick little tidbit about how this problem-solving process works. There were a lot of steps to what I just did, so I kind of want to explain. So the steps that you might take are the following, and these are outlined in the textbook, by the way, the online textbook. So you're going to want to draw a diagram quite clearly, and you're going to want to draw free body diagrams of isolated components of the system. So in our case, we did it for the 2 separate blocks. We could have also done a free body diagram for, the inclined plane, but we weren't interested in anything happening to the inclined plane, so we didn't have to include it. You're also going to need to choose useful coordinate systems. Now, useful is vague, but it's basically just choose coordinate systems that are natural for whatever object you're studying. And remember, you can choose more than one coordinate. You can choose different coordinate systems for different free body diagrams. And you're going to want to break forces up into components. That's what I did above. That's what I was doing when I found Fnet and Fnet in the X and Y direction. Then you're going to find Fnet, maybe in the X and the Y direction, and apply Newton's second law. Apply. Sixth step, apply any constraints that you might have. Remember, constraints are just equations that you get that are not related to Newton's laws. And then 7 is do the algebra. So these are, I mean, sometimes not all of these steps will apply, but these are useful steps in general. How do you relate free body, you mean FBD, how do you relate free body diagrams if the coordinate systems are different? The point is a free body diagram is just the forces on a particular object, but at least in this simple case, the acceleration in both cases was 0. So it doesn't matter what coordinate system you chose because the acceleration in any coordinate system is going to be 0. If the acceleration wasn't 0, you would just have to write the acceleration in different coordinate systems in different ways to represent the same thing. Because if you have a vector going down and you have, let's say this is the acceleration vector, and your coordinate systems are like this, you'll just have you'll have a component of ax and ay because you could break it up into 2 separate parts. Whereas if your coordinate system was up and down, then you would just have ay, for example. But as long as you're talking about the same vector quantities, it doesn't matter what coordinate system you choose. Coordinate systems are just a tool for making calculations easier. The mu stand for, that's the coefficient of static friction. Good question. All right, so the last thing to talk about before we move on to something completely different is, well, so far everything we've studied involves statics, i.e. nothing moving. So we're going to incorporate motion into these types of problems. So we're basically answering the question, what if the acceleration isn't 0? i.e. sometimes we might want to find the acceleration, or we might be given an acceleration and use that to find something else. So let's take the example as given here. So attach a spring to a rock, spring to a rock, and hold the other end. And then the idea is swing the rock around your head, like horizontally. The question is why does the spring stretch when flinging it around in a circle? So you might think that this is a silly question, but I pose to you that it's actually not, right? Because there is no force that actually pushes the block out, right? In order to get the spring to stretch, you have to apply a force to one end in order to get it to stretch, but no such force exists. So instead, there has to be something else happening. So first, let's just consider the block. So I'm going to draw a picture here. I'm going to do the steps. So here's a picture of the circle that's going around. Here's my hand. Here's our spring. Here's our block. So let's draw a free body diagram for the block at that position. So for our block, there's only one force acting on it. That's an elastic force. Right? It's just the spring pulling the block in. That's it. And I'm going to use the standard coordinate system here, x and y. So what we have then is we have that Fnet in the x direction is negative F elastic. Fnet in the y direction is 0. And so what do we have then? What is the acceleration here? Well, and let's assume that we're going this way. So remember, way back to like the third lecture or something, fourth lecture maybe, or maybe it was even the second lecture, we defined what the acceleration that an object undergoes when going around in a circle. That's the centripetal acceleration. So recall, the block has centripetal acceleration. That is the acceleration that it experiences, assuming there's, we're assuming there's no gravity and all that. So that means that the acceleration, magnitude of the centripetal acceleration, remember that that's v squared over the radius, right? So we can translate this. We know that the acceleration is in the left, it's towards the center of the circle. And so in our case, ax is just negative v squared over r. And so now we can write Newton's laws out, right? Apply Newton's second law. So we have F elastic divided by the mass of the block, say m, equals negative v squared over r. And so what do we find? We find that if v is not equal to 0, meaning if the object is moving at all, that means that the elastic force isn't 0. Well, what does that mean for the spring? Well, remember that the elastic force, sorry, this is the magnitude of the elastic force. The magnitude of the elastic force is equal to k times the magnitude of the displacement vector. So that means that delta x isn't 0, meaning that the spring is stretched. And we know that it could have been like if delta x isn't 0, it could have also been compressed. But we can use reason to argue that, well, if it was compressed, that means that the acceleration would have been in the outward direction of the inward direction. Yeah, no, you're right. I should have carried this down. That minus sign. I dropped the minus sign. Thank you for catching that. But the point still stands. The idea then is that there is an elastic force, and so that elastic force has to imply that the spring is stretched out. So what is it that causes the spring to be stretched? Well, the fact that the rock would just keep going in a straight line, if it were not for this acceleration that it undergoes due to the centripetal acceleration, is the thing that keeps it stretched out. You could also consider a third law pair here. The spring pulls the block to the center, which means that the block pulls the spring away from the center, and hence the spring is being stretched. We could do another example. We're a bit shy for time, so is this one worth doing? Yeah, but I'll just very briefly go over it. So here we're going to have another example where it's another object moving in a circle. Let's say I'm holding on to a string, and that string is attached to a rock that I'm swinging vertically in a circle, around and around like that. But the rock only barely makes it to the top. If the rock only barely makes it to the top of the circle, like it just barely arcs over and then it keeps going. But we have to require that the string remains at its full length, i.e. the string isn't going slack. Then we can ask what is the speed of the rock in terms of the length of the string. So let's draw a free body diagram for the rock at the top of the circle. At the top of the circle, there's mg going downwards. Let's just call this direction plus y and say this direction plus x. Mg goes downwards, and there are no other forces. And the reason there are no other forces is because the rock just barely makes it to the top, that means that there's no tension in the string anymore. The tension is precisely 0. So there's no force, there's no additional force going downwards from the rock or from the string. And so what we have here is that we have Fy is equal to m ay, and ay, again, centripetal, this is centripetal motion. Ay is just v squared over r. So what we get then is we get that mg equals mv squared over r. and we can then solve to get the velocity, i.e. the speed of the rock at the top of the circle. This is the square root of g times r, where r is the radius of our circle. So one of the tricks that I used here is I noted what the words I said was that it barely makes it to the top of the circle, and converted that to meaning something physical, i.e. there's no tension at the top. Because if it made it to the top of the circle with, but it could have been moving more slowly and still make it, then it would be, the string would be more taut and there'd be more tension. So the fact that it just barely made it there indicates to me that there's no tension. All right, so we're going to change gears pretty completely now. We're going to be talking about work and energy. So let's first talk a little bit about work. So for many problems, it's true that we only care about speed and not velocity, right? Like if I ask you, how long does it take for a, I don't know, a Ferrari to go from zero, or from rest, how long does it take for a Ferrari to make it from point A to point B in a straight line? It doesn't matter what's happening to the direction, we just need to worry about speed. So some cases, it's just worthwhile just to worry about speed and not velocity. And that will simplify problems, but we'll also lose information. And I'll explain what I mean by that in a minute. But in cases like these, we don't have to deal, or we don't want to work with vectors, because vectors are, they add complication to the problem that we might not need. However, Newton's second law is an equation about vectors, right? So we need some way to use Newton's second law in an alternative way that doesn't involve vectors. So let's consider, we're going to try to find that alternative method. Let's consider the components of acceleration. Remember when we did this, we had the perpendicular and the parallel components of acceleration. That's what we're going to be using here. We have that A is equal to, well, it's the time derivative of velocity, which is the time derivative of the speed times the unit vector for velocity, which is just dv dt in the velocity direction, plus v times dv hat dt. Remember that this was a perp and that this was a parallel. So note that a dot v hat, this is the component of the acceleration in the direction of the velocity, is dv dt v hat dot v hat. And if you're confused as to how I'm doing this calculation, go back and check the earlier videos I go over there. Plus v dv hat dt dot v hat. And remember that the time derivative of a vector dotted into that original vector, assuming their lengths don't change, that's 0. So this term is 0. This term here is 1. So this whole thing is just dv dt. So that is to say that the acceleration vector dotted into the velocity vector, that gives us the change in speed over time. So if we're interested only in changes in speed, then we are interested, or then it's enough just to consider a dot v. And so that's how we're going to use it. So now we need to talk, before we continue, we have to talk a little bit about kinetic energy and the work energy theorem. I mean, this is more of just a continuation of what we were just doing, but we kind of have to put aside that result there and go think about another part of the equation. Basically, the idea is of what we're going to do is we already have how Newton's second law is this. So what we're going to do is we're going to dot both sides by v and then do some more stuff to it, because then on the right hand side we'll have something that only cares about changes in speed, and so the left hand side will also only care about changes in speed. So now that we've established what to do with the acceleration, now we need to figure out what to do with the force. So first, I want to note that velocity is dl dt. So here, L is like displacement or position r, but it has a defined path. So in particular, I'll just give a quick example. If we have some path from, say, point A to point B, then maybe this is L of 0, this position here, a vector from the origin to there, whereas this position might be L of 10 or something, and this position might be L of 8. So you'll see that the vector L isn't just some variable, it's a well-defined path. And that's because the path can matter, right? Like, path can matter in physics. If you, well, I'll give a good example of why that matters later, but just keep in mind that L is just a position vector, but it's a particular position vector that changes in time, or it's a particular position vector that that's associated to the points on a well-defined path. Right, okay, so from before, like just now, we have v dv dt is equal to a dot v. Sorry, I'm missing a v up here. Yeah, so remember that a dot v hat is dv dt, but I want to know what a dot the v vector is, and so I need to multiply by the magnitude of v, because v is just v times v hat. That's all. So I'm just multiplying this equation through by the magnitude of v. Right, so we have v dv dt equals a dot v. Come on, behave well. And so I'm going to do something that you're not allowed to do usually. That implies that we have v dv dt equals a dot dl dt. So far, so good. This is all allowed. And then I'm just going to cancel out the dt's. Sue me. And I'm going to multiply by m. So multiplying by m, I'll just write this out so you guys can see it. This is the mass of the thing that's moving. We have mv dv equals a, or ma, dot dl. Technically, this shouldn't be allowed, but this is a physics class, not a math class. And then you'll see here that we have ma. This is fnet. So what we're left with is mv dv equals fnet dot dl. And now you might be asking, okay, but what is dl? Well, dl is just a vector between two very close points on a path. So maybe that's dl there, and maybe over here, dl is this vector. So dl is just a changing vector with infinitesimal size. And so now what we can do is we can actually integrate this. We can integrate both sides of the equation from, say, point A to point B. And so when I say from point A to point B, what I'm saying is so on the left-hand side, it's obvious because we're just integrating along a path that depends on A and B. On the right-hand side, it's obvious. On the left-hand side, it's less obvious, but just imagine that V changes with L. It changes at different points along the path, and that makes sense because the velocity can depend on where you are. Because where you are depends on what your acceleration was and what your velocity is. So there's a relationship there. But anyway, what you end up with is you get A to B, mv dv equals the integral from A to B, f net dot dl. And so what is this left-hand side? Well, this is just m times v times dv. So this is just 1/2 m, the velocity at point B squared minus 1/2 m, the velocity at point A squared. And that's equal to the integral from A to B of f net dot dl. And so this, let me move this down so then I have a little bit more room to write around it. Come on. My hand was not there. There we go, much better. There we go. Sometimes it doesn't like to behave. I'll just put a box around this and then I'll write next to it. This is what's called the work energy theorem. It's a mathematical relationship relating the force done applied over a distance, that's what this right-hand side is, to the change in the kinetic energy, that's what the left-hand side is. So 1/2 mvb squared minus 1/2 mva squared is the change in kinetic energy. And this integral is the work done by the net force. This is the work done on the object by the net force applied to the object. By the way, the fact that there's a dot product here means that only the force parallel to the path, only the force parallel to the path contributes. What am I hearing? Sounded like it came from my other computer, but that doesn't make any sense because they're both connected. Anyway, the point is that if I'm pushing on a block up, or better yet, let's say I'm pushing on a block down and to the right, and it's moving horizontally, only the component of the force that was actually to the right matters. Only this part actually contributes to the work. It doesn't matter how hard I push down because that's not going to do any work because the block's not moving. In that direction anyway. So in words, what we can say is that the total work done by all the forces acting on an object, that's what F net is, from a starting point to an ending point, i.e. points A and B, equals the object's change in kinetic energy between those same 2 points, i.e. work, which is abbreviated as W, or the total work abbreviated as W, from A to B is equal to delta KE. That's another way of expressing the work energy theorem. Basically says that if you do work, that energy gets put into another thing in the form of kinetic energy. So let's do a quick example. I'm actually going to open up a new page here. Oh, okay, so it's like, okay, it's gonna be white now. Nope, I didn't want another new page. That should speed up and make it cause less glitches. Let's just make those lines slightly less thin. There we go. Okay, so let's work out an example here. So let's say a car speeds up as it goes around a turn. You might ask, how does the change in kinetic energy I should back up one. I'll talk about this in a second, but I just want to go over one more thing. The units of kinetic energy can be found pretty easily. Let's just look at 1/2 mv squared. That's what kinetic energy is for some velocity. Mass has units of kilograms. Velocity has units of meters per second. So the units of kinetic energy are kilograms meters squared per second squared, which is also known as a joule, named after a guy. That's the unit of kinetic energy, and in general, that's the unit of energy, as in all forms. At least that's the standard SI unit. You'll see other units of energy elsewhere, like foot-pounds. That's the imperial unit of energy, and that's just because it's a foot, which is a distance, times a force, which is, or times a pound, which is a force. Right. So a car speeds up as it goes around a turn. How does the change in kinetic energy compared to the product of the magnitude of the accelerating force and the arc length of the turn? Meaning, let's say I apply some force. Well, we know a force has units of kilograms meters per second squared. That's a Newton. times a length, which has units of meters, that would also have units of joules. So the question that we're asking is the change in kinetic energy of a car going around a turn while speeding up equal to, greater than, or less than just multiplying the force by the length it traveled? The arc length times force times accelerating force. These are magnitudes, by the way. I'm talking about the magnitude of the accelerating force. I'll put it in bars. So we know that delta KE is just delta A, or is from integral from A to B of F net dot DL. That's what we just talked about. And the arc length, formula for arc length, hopefully you guys remember from calculus, is just the integral from A to B of just DL, right? This would be just like saying the length from like the distance. Is it possible to do an example with numbers instead of just variables? I mean, I don't have any worked, but you can imagine every time I write, and I will do a more explicit example in a minute, but you can imagine every time I write G that I have a 10 there, and every time I write M, I have a 2 kilograms there, or something like that, if that will be helpful. I'll do another, I'm going to continue to do examples though. So right, where was I? Arc length is just the integral of DL, because that's just adding up the lengths of all of those little infinitesimal lengths, right? If I just add up all these distances, this distance plus this distance plus that distance, that will give you the full length. And that's all an integral is. It's just adding up the little infinitesimal contributions. No, it's still misbehaving. I'll probably have to restart this thing at some point. So what is F net equal to? Oh, come on. F net dot arc length, or times arc length, I should say, is just the integral from A to B of the magnitude of F net times the magnitude of DL. And now, hopefully you can see why this is greater than the integral of F dot DL. Remember that F dot, or yeah, let's do it this way. F dot DL, well, that's equal to the magnitude of F times the magnitude of DL times the angle between them, cosine of the angle between them. And the cosine of theta is always 1 or less, right? So if you add up a whole bunch of contributions that are less than, if all of these are less than all of these, sorry, greater than all of those, then the integrals will be, the integrals will compare in the same way. And so what we find then is that this is equal to the change in kinetic energy, and so the change in kinetic energy is less than the product of the force and the arc length. The whole point of this exercise is it's not enough to just take the magnitude of the force and multiply it by the arc length, or by the length over which the object traveled, because except in a very few circumstances, that will get you the wrong answer. That's only true if the direction isn't changing, basically. And we know that the direction can change fairly often, so you got to be careful there. So the takeaway: work does not equal F net times delta x, or however you may have seen it before. Like that's only true in the simplest cases. It's only true when that less than or equal sign is an equal sign. So let me do an explicit example. Pushing a block at an angle. Across a rough surface. So there's going to be variables in there, but it's an explicit example, and you can just plug in the numbers at the end if you want. So we have our block. Say it starts, or we have our rough surface. Say it starts here. We're pushing our block at some angle. Maybe we're pushing down on it at this angle here. Maybe some angle theta, some force. And we are pushing it, so it travels this way, and it ends up, say, over here. And we assume that the force is constant. This distance, by the way, we're just going to call delta x, because it's just a name. We want to assume that f doesn't change with time. That's important because if it did, then the force would be changing with position as well, and so then the integral would become less straightforward. So let's figure out the net force. So we have our free body diagram. We have mg going down as always. We have kinetic friction going to the left because we're pushing it to the right. We have a normal force going up. And then we have our force that we are applying going down and to the right at that angle theta. So far, so good. And so we should probably give some coordinates. Let's use the standard coordinate system, x and y, say. So then what's f net? By the way, when we're working with work, it's just useful to write f net as a vector rather than looking at components, because we're going to need to take a dot product anyway. So this is f, which is the magnitude of the vector f, times cosine of theta. We're looking at this component now, minus fk in the I hat direction, plus n minus f sine theta minus mg in the j hat direction. So we have the normal force pointing upwards, right? Normal force is pointing upwards in the y direction. Mg is pointing downwards in the y direction. And then we have the vertical component. It's still doing the thing. Vertical component of the force that we're applying in the downwards direction there, which corresponds to this term. And that's the sign. That's why we have a sign there. So this is our force vector. So now what's the path? So remember, in order to do this vector, we have to know what path the object follows. So in our case, the object is only moving in the x direction. By the way, asking what is the path is akin to asking what is dl, the vector. So the object moves to the right. Which is the plus x direction. And so that tells us that dl, which is just a vector that points in the direction that it's going, that has an infinitesimal magnitude, is equal to dx, i.e. infinitesimal magnitude, times the unit vector I hat. So the path vector, the vector that points from that points all along the path little by little, has length dx. That just means it's an infinitesimal distance, and it points in the appropriate direction. So we're good. That dl labels or describes our path. So now we can compute the work. So the work from A to B, let me label this point A and this point B, let's say. We've defined that to be the integral of the integral from A to B of f net dot dl. So this is equal to, well, now you can plug in things. You get f cosine of theta minus fk in the I hat direction, plus n minus f sine theta minus mg in the j hat direction, dotted into dx I hat. So we know that I hat dotted into I hat is 1, j hat dotted into I hat is 0. So this leaves us with an integral from A to B of f cosine theta minus fk dx. And we know that the angle doesn't change with position, the magnitude of the force doesn't change with position, and the kinetic the kinetic force or the kinetic friction doesn't change with position. And so we can just factor these out. This is just f cosine theta minus fk times the integral from A to B dx. And now this is one of the few cases where now you can just multiply. Actually, no, it's still not one of the few cases because the magnitude of the force is different. This here is the arc length, that's the path length, that is just delta x. So our work done here is f cosine theta minus fk times delta x. So that is the work. Now, we are almost out of time, so I'm just going to make a very quick remark. So Newton's second law, n minus f sine theta minus mg, or do we have to use the dot product? Perhaps I don't understand your question. Let me make this remark and then we can talk about it. So the work energy theorem can solve problems fairly easily. Like, for example, if we knew the initial speed, we could plug in the initial speed and the mass and the work done in the work energy theorem to find the final speed. It does greatly solve problems, or it greatly simplifies problems where we're not interested in it. However, we are losing some information. For example, we don't learn anything about the direction the object's traveling in, because all the work energy theorem tells us about is the change in speed. Similarly, we don't learn anything about duration. The work could have been done very slowly, but for a long time, or it could have been done very quickly, but for a short time, and we don't know anything about that either. In order to solve problems that involve duration or changes in direction, you might have to use the work energy theorem and some stuff about forces and Newton's laws. Right, so that's where I'm going to call it today. Let me stop recording.